We can now move a little bit deeper into graph theory. We've spent a lot of time on definitions. In our last video, we were able to start actually thinking and problem solving a little bit with graphs. This section, 11.3, we're going to go through Euler trails and circuits. So we talked at the end of our last video about vertex degree, or the degree of a vertex. And the degree of a vertex is the number of edges that are incident to that vertex. So for this particular example, this degree of A, which notice the notation that we'll use, is 3 because there's 1, 2, 3 edges coming out of it. It doesn't matter that one of them is a loop. Whereas B, the degree of B, is just 1 because there is only one edge coming out of vertex B. Again, we talked before that each time we draw an edge, it's going to add 2 degrees because obviously it has to connect with 2 vertices. Whether that's the same vertice twice or 2 different vertices, it doesn't matter. Every time that we add an edge, we're adding a degree of 2. Again, I'm not going to go through that proof with you. It is in your textbook, or you can certainly Google someone else going through that proof with you. Let's take a look at something called a regular graph, or an n-regular graph. A regular graph is a graph where the degree of each vertex is equal, essentially. So if it was a 2-regular graph, each vertex would have a degree of 2. A 3-regular graph would have each vertex with a degree of 3, etc. So it's helpful, obviously, to keep in mind that every time I add an edge, it adds 2 degrees, but it also is helpful to keep in mind that if I need to add 1 degree, I would add that degree, or excuse me, add that edge to that vertex and another vertex. And if I wanted to add 2, then I would add a loop. So for instance, here's an example of a graph that is not regular, because this has a degree of 1, of 2, of 2, and of 1. And the question is, can I make this a 3-regular graph? So can I? Well, I could add another edge connecting B and C. That would make this 3 and 3. And then I could just get crazy and add a loop to each of these, which would make this 3 and 3. So this could be now a 3-regular graph. Is that the only way I could have done it? No, of course not. I could have done it other ways, but the question has now been answered. Yes, I can make the graph 3-regular. Here's a question for you to try. Is it possible for me to draw a 4-regular graph that has 10 edges? Now, you can either go about this an intellectual way and use some of those things that we know about vertices and degrees and edges, etc., or you can just plug and chug, which means try to create a graph and see if you can make it work. Either way, I would like you to try this question. When you're ready, press play to see how you did. So I'm not really one for guess and check. I'd like to have the math behind it so that I know if I'm wasting my time or not. So here's how I would go about this question. We're using the fact that if I add up all of the degrees, it equals 2 times the number of edges. Well, why does that matter? Because they specify 10 edges. So I know, based on that, that I should have a total degree of 20. So if I add up the degrees of all the vertices, it must be 20. Now typically that wouldn't tell us how many vertices I must have, but because it's 4-regular, we're saying that 20 has to have 4 per vertex, which means 5 vertices. So if you'll notice, now that I know it is possible, I've given you 2 different representations, and both of those representations have 5 vertices, and both have a degree of 4 for each vertex. And so yes, this is in fact possible, and I've given you 2 different ways to do it. Before we dive into Euler trails and circuits, I want to take just a quick detour for all you computer people out there. I am not a computer person, for the record. I don't do networking, I don't do programming, I do none of that. But let's talk a little bit about the math that would go into that, because some of you are computer people. So a hypercube is used in computer architecture in order to build a parallel computer where essentially you have several computers all working on the same problem. Let's talk about the math behind this. We want to create a loop-free, meaning I don't want a computer connected to itself or networked with itself. Connected undirected graph where each processor is assigned a vertex. So all of these little pink guys, which I don't have pink right now, so all of these guys are all computer processing units. You get the idea. I want to create a graph that's going to speed up processing time. So example, if I were adding another computer, this wouldn't really help because to get from here to here, it's going to take an increasingly large amount of time. So every time I have more distance, the processing time increases. So instead of creating this very, very long line of computers and processors where the processing time would continue to increase and increase, we're going to look at this more in a three-dimensional way. And again, I'm going to now be dealing with Qn, and Q just denotes that it's a hypercube. And essentially what happens, we'll start with Q1. Q1 has essentially two processors that are directly connected, 0 and 1. Now what I'm going to do to create Q2 is make this now 0, 0 and 0, 1. And again, this is just binary values. And then create a copy where my first digit is now 1. So 1, 0 and 1, 1. And again, note how they are connected. To create Q3, I'm taking this guy and I'm sticking a 0 in front of each of those values. That's here. And then I'm creating a copy of that, which is this guy, and putting a 1 in front of each of those values, and then connecting them. And you can see that I could continue that pattern for Q4, Q5, etc. Here's another example. Obviously, this is Q4. So Q4, because I have now 4 values, and we're still using this same idea, but now I can really sort of rearrange it and say that the number of edges is 1/2 n times 2 to the n, since each vertex has a degree of n and there are 2 to the n vertices. Moving away from hypercubes and things I know nothing about, let's look back at one proof before we talk about Euler trails and circuits and back to the 7 bridges of Königsberg problem. Let's take a look at a proof, just because we haven't looked at any proofs yet in this section, and prove that there must be an even number of odd degree vertices in any undirected graph. So we've really only dealt with undirected graphs, and we're saying there must be an even number of odd degree vertices, which we haven't really talked about. Now obviously you could look at examples, you could try to create a graph. There I've got 2 that are odd. Let's add another loop here. This is 2 that are odd again because this is 1 and this is 3. So let's connect the dots. Well, now this guy is 4, so that's even, but now this guy's odd. So again, I still have 2 that are odd. So you can continue to practice and try, but remember that that's not a proof. That's just a way for you to understand the concept in your head. So let's take a look at an actual proof, again using what we know. So we know this, the sum of all of the degrees is equal to 2 times the number of edges. And because we've done this before in other proofs, we know that we're going to represent something that's odd by 2 times some value plus 1, because then we know 2 times that value is even, adding 1 makes it odd. So let's assume by contradiction that in fact we have an odd number of odd degree vertices. So the number of odd vertices we're going to represent as 2k plus 1. the degree of the odd vertice is 2k plus 1, and the number of those vertices is 2n plus 1. Again, both of those are odd, so an odd number of odd degree. And then the remaining vertices would all be even, and so the remaining vertices will just represent with m. So if I had some graph with these properties and I added up the degrees, I would take the number of odd vertices times the degree of those vertices. That's right here. And I would add to that the degree of the even vertices, and that would have to equal 2e. 2e because of my theorem, or my definition that says if I add up all of the degrees, it's 2 times the number of edges. So let's FOIL this baby out and get here. And I notice that these values are all even. So I can factor a 2 out. So 2 times all of this plus 1 is equal to 2e. Well, that doesn't work, does it? Because this guy is even because it's 2. Sorry, this whole thing is even because it's taken times 2. This whole thing is even because it's taken times 2. So the fact that I'm adding 1 on this side means that that is not going to be mathematically feasible. So again, this is impossible since the left side must be odd, because the left side is 2 times some value plus 1, and we know that this means odd. So again, we have just proved this by contradiction. So this is a video on Euler trails and circuits, and I've spent about 12 minutes talking about anything but Euler trails and circuits, so maybe we should get down to it, huh? Let's think back to 11.1 when we learned about the definitions. What's a trail? What's a circuit? Because obviously if we're going to look at Euler trails and circuits, we need to remember what's a trail, what's a circuit. A trail is just a walk where we haven't repeated any edges, and a circuit is a trail where I begin and end at the same vertex. So we're going to look at Euler trails and circuits. So we're going to let G be a graph, an undirected graph with no isolated vertices, meaning I don't have any guys out here by themselves, not connected. G has an Euler circuit or trail if there is a circuit or trail that traverses every edge exactly once. So again, where does this come from? Well, if you'll remember back in section 11.1 when we first talked about this, we were looking at the bridges of Königsberg problem, and we said, can we walk through the city and walk over every bridge only once? So that's what Euler was interested in, is can I traverse every edge only one time? And edge, in his case, was bridge. So that is where all of this originated from, is that bridges problem. So for instance, if I'm looking at this particular graph, I could go from A to B to C to E to D to C to A. Now, does it matter that I visited C more than once? No, because we're talking about edges. Did I repeat an edge? No. So this, in fact, would be an Euler circuit. Circuit because I began and ended at A. What Euler found is that a graph will have an Euler circuit, again, one where it begins and ends at the same vertex, if G is connected, which means your graph is connected, we have no isolated vertices, and 2, every vertex has an even degree. Now let's pay attention to this one, because even degree implies the Euler circuit. Also, we can say that if it's an undirected graph or multigraph with no isolated vertices, then we have a trail if G is connected and has exactly 2 vertices of odd degree. So a trail has exactly 2 vertices of odd degree with everything else even. A circuit has every even degree. So there is a formal proof for each found in your textbook, page 534, 535, of Discrete and Combinatorial Mathematics, 5th edition by Grimaldi. But again, just reasoning through it, if this is true, then it certainly makes sense that we can take an Euler circuit and turn it into an Euler trail by essentially taking out one edge and then making the trail go from the one first odd vertice or one of the odd vertices to the other odd vertice. So looking back at the original problem that started all of this, looking at this node or vertex, I have a degree of 3. This has a degree of 3. This has a degree of 3. And this has a degree of 5. So we can see we have 4 vertices, all of odd degree, and therefore, based on Euler's studies, we know that in fact it's not possible to cross each bridge only once and return to the starting point, because essentially what he was asking is, can we have an Euler circuit? An Euler circuit because we're beginning and ending at the same point. Let's shift our focus just a little bit to a directed graph instead. So I'm going to make up a little directed graph. Let's say I've got one going from D to A, from A to B, from B to C, from D to B, and we'll stick with that. So when we're looking at a directed graph, we don't just say A has a degree of 2, we would say A has an in degree of 1 because we have 1 going into A, and an out degree of 1 because I have one edge going out from A. Similarly, B would have an in degree of 2 because we have from A to B and from D to B, and an out degree of 1 because we have 1 going out to C. C would have only an in degree of 1, no out degree because C is not connecting outwardly to anything, and D would have an out degree of 2 because D is only going out. So again, the total degree is just the sum of in degrees and out degrees, and we can still say that the sum is going to be even. So it's the same concept as before whenever we add an edge. In this case, an edge would be one in degree and one out degree. So this edge right here gives me an out degree on A and an in degree on B. So again, it makes sense if I take my 1 plus 1 is 2, plus 2 plus 1 I have 5, plus 2 is 7, plus 1 is 8, so my total degree in this case is 8, and again we notice that's an even value. So why are we talking about directed graphs? Because if we want to find an Euler circuit on a directed graph, that will occur if and only if the in degree of each vertex is equal to the out degree of each vertex. So obviously the little picture that I've drawn here not going to work. A does have that where the in degree of 1 equals the out degree of 1, but obviously B, C, and D all do not. So a very simple example, probably too simple of an example, would be one that looks like this. Each of those vertices, A, B, C, D, has an in degree of 1 and an out degree of 1 because they equal, and again, they don't all have to be of 1, they just all have to be equal to one another. So the in degree of each vertex. So this is for all vertices that belong to the set of vertices. Have to have the in degree of that vertice equal the out degree of that vertex. So here's an application of particularly an Euler circuit where I begin and end at the same place. Again, there is no Euler circuit on this page, so you might be thinking I'm crazy, but my question here is that I have this drum that rotates, and we can see it's rotating in this direction. And I've got 3 connectors, and what's going to happen is it's going to give me a readout based on the values that I put into my figure. So this particular one would be 1, 0, 0. That's the output. If I then rotate the drum, let's say I put a 0 here, and I rotated it 1, then instead of 1, 0, 0, I would have 0, 1, 0. And the question is, how can I label the numbers on my drum so that each time I rotate, I get a different 3-bit string? So again, what 3-bit strings am I talking about? I'm talking about 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, 1, 1, 1. These are all of the different possibilities. Remember, 2 to the third, it's either a 0 or a 1, and there's 3 places. So these are all of the 8 different ones that I want. So I have a choice. I can just guess and check, start filling in numbers, see what happens, or, because we're talking about Euler trails and circuits, I can use a more scientific way and create a directed graph to help me determine this solution. For an 8-bit string, we must have 4 vertices, and here's how it's going to work. In order for me to connect 2 vertices, again, this is directed, and directed is going to be important here because not all of them are going to connect in each direction. Most of them will not. In order to connect 2 vertices, I need the middle digit to be the same. So for instance, 0, 0 can connect to 0, 1 because their middle digit of 0 is the same. So I can connect in this direction. So essentially, in order for 0, 0 to be connected to something, it must start with a 0. So the only thing I can connect to is 0, 1 and back to itself, because obviously that starts with a 0. Now let's take a look at 0, 1. Obviously I'm ending with a 1, which means my first digit must be a 1. So I cannot connect back to 0, 0. But I can connect to 1, 0 because it begins with a 1, and to 1, 1 because it begins with a 1, but I cannot connect it to itself because it begins with a 0. Let's move on to 1, 1. 1, 1 ends with a 1, so anything that starts with a 1 I can connect to. So I can connect to 1, 0, and I can connect to itself because it begins with a 1. Lastly, looking at 1, 0, it's ending in a 0, so anything that begins in a 0, like 0, 0, or 0, 1, I can connect to, but I can't connect to itself because it begins with a 1. So here is now my directed graph, and the question at this point will be, from this directed graph, based on what we know about an Euler circuit, is can I come up with an Euler circuit based on this directed graph? And that is what I'm going to leave you to do. So take the graph that we just created, hopefully you wrote it down. If not, rewind the video, write down that directed graph. Make sure that an Euler circuit can be created, and then use that figure to create your directed graph here. When you're ready, press play to see how you did. Alright, let's take a look. So, how do I know how to do this? Well, I want to create, essentially, an Euler circuit. So how would I create an Euler circuit? First of all, I would verify that an Euler circuit can be come up with, and that is by saying that the in degree is 2, and the out degree is 2. So they're equal to each other. Here the in degree is 2 and the out degree is 2. Here the in degree is 2, the out degree is 2, and here the in degree is 2 and the out degree is 2. So it doesn't matter that they're all 2's, it matters that these two match up, these two match up, these two match up, and these two match up. Because that is true, we know, based on Euler's work, that yes, I can find an Euler circuit. So how am I going to find it? there's more than one correct answer because obviously this is a spinning drum. So I have chosen to start here at 0, 0. And I went this direction first, so I went from 0, 0 to 0, 0. And then I went to 0, 1. And then I went to 1, 1. And again, there's more than one correct answer. Then I went from 1, 1 to 1, 0. No, just kidding. I didn't want to miss my 1, 1 to 1, 1. Then I went from 1, 1 to 1, 0. Then I went from 1, 0 to 0, 1. Whoops, I went the wrong arrow to 0, 1. I went from 0, 1 to 1, 0. And then from 1, 0 to 0, 0. So as you can see, I've crossed every path once and only once. I started at 0, 0. I ended at 0, 0. Now, again, how did that help me to solve this problem? Because now I have my correct 8-bit string. Where did it come from? I had 0, 0 to, oh, my pen's not working, 0, 0 to 0, 1 to 1, 1 to 1, 1 to 1, 0 to 0, 1 to 1, 0, and then this one would go back to the beginning. So this guy right here, my 8-bit string, I could put on here in any order. So I started here, 0, 0, 1, 1, 1, 0, 1, 0. That's where I started, is here. But it really doesn't matter where you start, because as long as I'm putting them in this order, obviously this is a circuit that would continue to go forever and ever. So essentially, as long as you find this string, I could have started here and said 0, 0, 1, 1, 1, 0, 1, 0, and still been absolutely correct.